Okay, so we're back and we're gonna start with the rules of equivalence today. But before we go to rules of equivalence, let's just revise doing like a proof, like a derivation, um, more like a proof of like the argument being valid using the first four rules of inference. So I'll just write down um, the question. Uh, oh shit, I have to scroll all the way down. Okay. Um, let's try. So we have A and not B implies C implies D. Second premise, um, A and not B or D implies not C. Not C implies D. Uh, not C implies A. Wait, I should write that in one. Is there a fifth premise? No, there's a conclusion. Um, okay, let's try it. So this is A. Okay, I'll just rewrite it in case it's. This is also A. I'll also rewrite this. Let's go.
I'm just gonna work through it over here, okay?
Yeah, and you can also like tell me whatever the like once you figure out like a step, just tell me the step.
Okay, because normally I'm pretty slow, so
Yeah,
I just need some time.
you can think out aloud. It's fine.
Okay. I'm not that good at thinking out loud, unfortunately.
Okay, okay, yeah, that's fine.
So, so for number five,
Mm-hmm.
I think there could be a modus tonans.
Okay.
So not,
Mm-hmm.
and then brackets, A and not B, and then one, two.
Okay, one sec. Okay.
Yeah, that's what I've got for the first bit. So I'll see what I can do now. I think for 6 we have a disjunctive syllogism.
Okay.
So D implies not C. And then I'm doing this on premise 2 and 5.
Okay. Premise 2 and premise 5. Mm-hmm.
Mm-hmm. And I think there's for 7 a hypothetical syllogism.
Mm-hmm.
So it's D implies A. And then I'm doing this on premise 4 and 6.
Premise 4 and 6. Okay. Yeah.
And then that means we've got what we want.
Yep.
So we write QED at the end.
Yep. Okay. Yeah, that works. Yeah. Yeah, with practice and with seeing more and more like arguments and stuff, I think you'll get the, you know, you'll get faster at doing all of this.
So I don't need to see the first 4 rules at the moment.
Yeah,
I can do it. Just need to get used to the patterns.
exactly.
And I don't want to go too fast and make a mistake.
Yeah. I mean, you can also like sort of, I guess, challenge yourself to develop speed or something. Like it's okay if you make errors, but yeah, I think you get the point.
So yeah, that was using the first 4 rules.
Mm-hmm.
In the last lesson, we also covered 4 other rules.
Yeah.
Well, 3 actually.
Yeah. No, we covered
No, 4,
four.
4,
Yeah.
4. Yeah.
Conjunction, addition, simplification, constructive dilemma, and there's like two of both, two of simplification and two of, you know. Well, this is technically one, but like there's two versions of constructive dilemma. There's two versions of, like, one is a modus ponens version, and one's a modus tollens version. Um,
Yeah, and I had a look at the constructive dilemma, and I think it makes sense to me how it's like constructed.
Yeah. Yeah, like once you sort of ponder over it, like it eventually sort of clicks into place. Uh,
Mhm.
yeah. Okay. So then let's move to uh, rules of equivalence. So, rules of equivalence again, they are like rules of propositional logic, but they're not. They like you can think of. Okay, they're also called rules of replacement, right?
Okay.
Yeah. So they're called rules of equivalence or rules of replacement because they are certain patterns. There are certain patterns that you find in propositional logic, which obviously, if you draw a truth table, you can prove that they are like sort of equivalent. But it's like there are certain patterns that appear throughout propositional logic, so they have sort of um, like sort of compiled them as like a list of rules, um, and there's like a name given to each of them, and then you can just like whenever you are doing some kind of substitution or like replacement or then you can just call that, like how you're saying this is true by modus ponens, you can also say this is true by some replacement rule. um, yeah. So
Hmm.
yeah, like long and short, they're sort of like patterns of there's like you can think of them as pairs. They are pairs of propositional forms like structures, which are interchangeable. Like you, whenever you see one, you can use the other. So it's like um, so one sec. Let me just use. So you have form one.
So a bit like in algebra when you know like the differential of something is something else
Yeah,
and you don't want to do the proof. So you
exactly.
just
Yeah, exactly. It's sort of like a shortcut. Um, okay, so
let's
this
say
is yeah, this is sort of the structure, right? Of these rules. So you have form one, and you have form two, and this okay. Note that this looks like a biconditional symbol, right? Um, but this actually is not a biconditional symbol. Um, this is, it looks the same, but this is actually a metalinguistic uh, operator. You know how we had metalinguistic variables like alpha to represent any kind of um, formula, and you also had beta to represent any kind of formula. This symbol, which looks identical to a biconditional, is also like a metalinguistic, symbol or a metalinguistic operator. And this just means so this symbol is called a logical equivalence symbol. Um, so some people also draw it like this. Uh, you know how in chemistry you have
hmm.
like a reversible reaction. Some people draw it like that, and the reason like some people like to draw it like that is because whenever you see form 1, you can replace it with form 2 if the proof calls for it, and whenever you see form 2, if the proof calls for it, you can replace it with form 1. So they're sort of like reversible in in that sense. So that's why some people use this symbol to represent, they use this to represent the metalinguistic symbol, as opposed to using the this, so as to not confuse between like a biconditional symbol. So like going forward, we'll be using this. Okay. Um. Okay. So let's start with the first one, which is called De Morgan's law.
I think we covered this. Well, we briefly glanced over this one.
Yes, we introduced this when we talked about the material implication. We'll go over that again. Um, but yeah, so this is De Morgan's law. It's a rule of replacement. There are two forms of, you know, De Morgan's law. The first form is alpha and beta. Okay, this is the first form. And the negation of alpha and beta can be replaced with not alpha or not beta. So to make sense of this, you can just think about the truth table of a conjunction, right? So when we say alpha and beta, we mean that the conjunction is true. When we say not alpha and beta, we say that the conjunction is false. And a conjunction is false when at least one of the disjuncts when at least one of the conjuncts is false. So either this is false or this is false or both of them is false. Note that this is like an inclusive disjunction, right? um,
Hmm.
so whenever you see this, right, whenever you see alpha and beta, the negation of alpha and beta, you can replace it with this. To also give you an intuition, this is also sort of like multiplying something inside a bracket. Like if you have like 2 3 plus 2, something like that, right? um Wait, not this. Does that work? 3 to the 6 plus. Yeah, I think that also works. So if you have this, so it's like 2 into 3 plus 2 into plus 2, 2 into 2, sorry. So that's like 3 to the 6 plus 4 equal to 10, which is basically the same as, like, 3 plus 2 is 5, 5 to the 10. So it's like you're distributing this here and here, right? So it's a bit like that. um, I don't know if that makes sense, but you can sort of think of this as like, okay, so here you have this conjunction over here, yeah, and you're distributing this here, you're distributing this here, and this gets flipped. Okay, so like this gets distributed, so the negation attaches itself with the alpha, it also attaches itself with beta, and it sort of flips the conjunction symbol to a disjunction, right? So that's one way to sort of look at the, like the first, the conjunction form of De Morgan's law.
And
uh, yeah,
if I just explain back to you what you said before this,
sure.
the last way. So you're saying that when the conjunction of alpha and beta is false,
Mm-hmm.
this is when not so one So that there's it's an inclusive disjunction on the right hand side, right?
Yes, yes.
So so even if they're both false,
Yeah.
so as long as one of alpha or beta is false, then the one on the left hand side will be false, right?
Yeah. So think of the conjunction table, right? So this is the table for conjunction. It's only true when both of them are true. So whenever there's like the first one is true, the first one is false, then it is false. The second one is false, then it is false. If this one is false, if both of them are false, then also it is false. So you have like a an inclusive disjunction of all the of all the propositions.
Hmm.
So that's yeah. So that's why it's sort of like um, yeah. That's why it works. And you can prove it by like drawing a truth table. I can show the semantic equivalence, like the logical equivalence, um, by using like a truth table.
Could we
Um,
do that quickly?
yeah, sure.
Yeah.
Um, I'll do a shortcut. Okay, so this is the table for a conjunction, right? The
Yeah.
negation will be F T T T.
Yeah.
Um, the negation of this thing will be negation of alpha will be what F F
Uh,
T T. Negation of
yeah.
beta will be F T F T, and then the disjunct of this will be F. um, the disjunct okay, this is a disjunction, so this is true, and this is true. See this, both of them are equivalent.
Yeah.
Yeah, I just did like a shortcut. Yeah, like you can imagine this. So you can also do it yourself at this point. Um,
Hmm.
but yeah, that's how it works. That's De Morgan's law. That's the first one of De Morgan's law. There's also a second one. Can you guess what it is?
Is it going to be negative negation of alpha or beta?
Yeah.
And then I'm guessing it's going to be the same thing, not alpha, and then and not beta. If you
Yeah.
flip it again.
Exactly. Exactly. I think you're getting the drift, right? This is easy. Um, So yeah, that's basically De Morgan's law. So there's like one version which goes from like a conjunction to a disjunction, and there's one version which goes from a disjunction to a conjunction. Okay.
Mm.
Yeah, it's very simple. So then we'll just go to the next one. Like, uh, let's not wait for anything else. The second one is called association. Okay. And this also has two versions. uh, 2.2, right? 2.2. So you have alpha, one sec, alpha,
2.1, right?
sorry, yeah, 2.1. Okay, yeah. So you have alpha or beta or gamma. Okay, so that's basically it's like when you have um, two disjunctions, you can basically move the bracket around and it's gonna be the same thing.
Yeah.
Yeah. So that's just
I don't think.
association. And what do you think is gonna be the second one.
Uh, Same thing, but with yeah, conjunctions.
Exactly. Again, like you can just draw like a truth table and prove this and all of that. Like if you want that, you like if you want, you can sort of like look at it. Um, Actually, you know what? Let's try to. Uh, Nah, we'll do that later. Yeah, because like three variables is a big table. Um, but yeah, like, is there anything that you find unintuitive here? Because like this is like straightforward stuff. So if you like, if there's something unintuitive that I can like go into like sort of trying to explain it. Like, is this fine? Hello, hello. I
Yeah,
Okay,
yeah.
okay.
Hello.
Yeah, I can hear you now. I wasn't
Yeah.
able to hear you for like the last 10
No,
20
sorry,
seconds.
I had my mic on mute, but yeah, it's pretty intuitive. I think I would be able to prove that
Yeah,
if I had to during yeah, using truth tables.
yeah, exactly. Okay. Now this one maybe like the next one is called. Oh, sorry. It's called distribution. Can you guess what this might be? Just from the name. So I'll just give you a hint that it's all gonna be like alpha, beta, gamma again.
No idea.
Okay. Yeah. So this one is gonna be like alpha and beta. Okay, and you have a disjunction. So it's a combination of conjunctions and disjunction. Okay. And what do you think you'll get? Okay, just from the name, can you try to guess what the replacement is going to be?
Distribution, I don't know. I would guess you just move the brackets as you did in the last go.
No, that wouldn't work. But because we have to distribute this, right? So we have to distribute this. So what's gonna happen is you get alpha and beta. Okay. So what you're doing is you're pairing these two. Okay. And then you're pairing these two. So this is going to be separated with a disjunction, and then you have alpha or gamma. Does it make sense now? Like the word distribution, like you're distributing this inside the bracket.
I see, yeah.
Yeah.
So you're splitting up alpha sort of.
Yeah, you're distributing alpha to each of the disjuncts. So you're like giving the alpha and to beta, and you're also giving the alpha. Sorry, yeah, this is gonna be an alpha and.
So
Yeah.
it's an and in both brackets.
Yes. And then like you're just gonna use like the disjunction inside to connect both of the distributed like things. So you have like this one, these two, and then you have these two, and then you're gonna separate them with the disjunction.
Makes sense.
Yeah. So let's do 3.2. Can you guess what 3.2 is gonna be just based on this?
I'll guess that it's alpha disjunction and then beta
Uh huh.
or and gamma.
Okay. And what's going to be the replacement?
And then it will be alpha or beta,
Yeah,
close brackets, and alpha or gamma.
exactly. Yeah, so that's distribution basically. Um, so you need to be careful about this because like this looks very similar to the association rule that we learned here. So gotta be very careful about what the symbols are and apply the rule accordingly because if you apply association here, that won't work.
Hmm.
Yeah, and yeah, you can try to prove that with like a truth table and all of that. Um, but yeah, so you got distribution, right? We can move to the next one. We'll do four this time. Like we've done three. There's one more that we can do, and maybe a few problems.
Yeah, let's move on to 4.
Yeah. So this is called commutation or commutativity. Sorry, I suck at writing. Yeah. Okay. Okay. This one is also going to have two variants. Um,
So commutativity, right?
yeah. So this is also going to have two variants. Commutativity simply is that's all.
Okay.
What's the next one? Guess the next one.
Yeah, just the same thing, but with a conjunction.
Yeah.
This one's okay.
Yeah. It's not as difficult as rules of inference, but yeah. What? So we've shown that disjunctions and conjunctions are commutative, right? Which other operate? There's one more operator which is commutative.
I would say uh conditional.
No, conditionals are not
Uh, I mean biconditional.
biconditional. Yes. So biconditional again is a symmetric sort of a operator, right? Which is why biconditionals can. So you can apply commutativity to biconditionals as well. Um, we will discuss that. Like I can
Like
just add it over here, but there's a
I
separate
just
section for bicondition, a separate section for rules of inference and equivalence which process biconditional. So we'll like sort of keep it until then.
okay.
Yeah. Okay, so I guess we can do like a fun activity now. So we have done four of these rules, right? Let's do something fun. Okay. what's this?
So this I'll just use this is rules of inference we're doing,
Yeah.
right? You want me to solve it, so then it'll just be uh create a new premise and then just show that I use what was it again? The word for it uh modus ponens.
Right. So how do you prove modus ponens is valid?
So I would um to prove it that it's valid, to go back all the way, we will do it using truth tables, right?
We can use truth tables. Yeah, that's one way to do it. That's like
That's
a yeah. But like if you want to do it with like a natural deduction, how would you do it without using truth tables?
so using the rules of inference.
Yeah, rules of inference, rules of replacement.
So then I'll just put a new premise free, right?
Okay.
And then I'll write Q, and then 1, 2 modus ponens, and
No,
then
that's not gonna work. So you're trying to prove modus ponens is valid, right?
yeah.
So you can't use modus ponens.
Mm.
So you can use anything other than modus ponens.
So
I'll give you a hint, okay?
yeah.
Um, the hint. Oh wait. Yeah. You know what? Yeah, we'll do this exercise later because the. Okay. Okay. Fine. I'll give you the hint. Okay. So this is not P or Q. Um, this is just one. We haven't done this, but this is yeah material implication. Okay. What would you do?
How we done? Wait, material implication.
No, we haven't. We'll do it next time.
Okay. So so you did an extra rule which I don't know.
Yeah, that's fine.
And
So I'll just give you that as a hint, right?
okay, so now what do I do? Do I do use the rules of inference, or
Yeah, you can do that.
so from there then it would be it would be like a disjunctive syllogism, right?
Okay. So what's the conclusion?
So then it would Q.
Q and disjunctive syllogism on which premises?
So I did it on 2 and 3.
2 and 3. Okay. Yeah, this one modus ponens we should have done next time. I didn't remember that I hadn't done um, material implication.